Alright, so now we have to talk a little bit about boundary conditions if we're going to solve these beam deflection problems. So if you don't really remember boundary conditions from calculus because it was so long ago, don't worry. You'll always be able to use your phone a friend lifeline. So I got my phone out here. Just call up, 1-800 help me with calculus, and we'll talk about boundary conditions. Yeah, I need some help on boundary conditions. All right, so if we recall from calculus, boundary conditions are what we need to solve for constants of integration. So we know that our relationship, we have a fourth derivative relationship, and when we integrate that back, we're going to get some constants of integration. But we can't just make these constants up. We actually have to pull them from our understanding of engineering mechanics. So let's take a look at the boundary conditions for some of our beams. So our first boundary condition from statics is like our pin and our roller. So I've gone ahead and drawn a pin and a roller and a little XY coordinate system. And this dashed line is the deflected shape of the beam. Okay, and so that's going to be a function y of x. When we go through and calculate deflections using the method of integration, I want you to be thinking this is a very mathematical approach. We're kind of taking the beam and modeling it in a XY coordinate system to solve. So we know that the deflection at the pin or the roller would have to be 0. So we would say that we have y of 0 equals 0. And that's one of the boundary conditions that we have for this particular case. So it just means the deflection at the pin or roller is 0. Likewise, we can come up with the different boundary conditions for moment. If we remember back to our moment diagrams, for pins and rollers that also were at the end of the beam, our moment was 0. So we could say m of 0 equals 0. Or from our relationship, that is EIY double prime of 0 equals 0. So again, I want to caution you that this is only true if the pin or the roller is also at the end of the beam. Otherwise, the moment is not 0. So I'll put a little warning sign in there for you. Moving on, the next conditions we'll consider is a fixed end. So when we look at a fixed end, we set up our XY coordinate system starting at the left-hand side. We know that the deflection at the fixed end is also going to equal 0. So the next boundary condition is y of 0 equals 0, and that just means that the deflection at a fixed end is equal to 0. Now we could consider the moment. What is the moment at the fixed end? Well, we know the moment has a value. There's a fixed end moment at that point. So if we go through statics, we have a fixed end moment. So we can't do anything really with the moment or maybe the shear. However, for fixed ends, the slope has to be 0 at the support. So when we fix something, we're really grabbing that beam and we're holding it and we're preventing it from rotating at the very end or having a slope. So the next boundary condition is y prime of 0 equals 0. So remember, if y is the deflection, the derivative of deflection will give us the slope of the beam. Moving on, let's take a look at a case where we have a beam with some sort of distributed load on it. And I'll just kind of take this to an end. If the support is located at the end and we have some sort of reaction, we could set up some of our boundary conditions in terms of this reaction. Namely, we would have in this case that the shear at 0 would equal whatever the reaction was, because we know that reaction will cause an immediate jump in the shear, and then the shear will then start going down because of that distributed load. So shear is related to the third derivative of y, as we saw in our notes. So we'll keep that in mind. EI y triple prime is going to be equal to the shear. The shear at 0 would be the support reaction. All right, finally, I want to consider a beam that has a free end, but that the free end is not at the support. So let's just say we have some distributed load on a beam. Who knows how long this beam is, but it goes over a roller and then it continues on a little bit and then goes to an end that is now a free end. By free end, I just mean that there's not a support reaction at that point. So I sketched in green kind of the deflected shape of this beam over this support. And so we can write a few different things. If we're thinking about the free end, the moment and the shear at that point has to be 0. So we know our shear and moment diagrams have to close out to 0. And so if there's no support reaction or no any kind of external forces at that point to get us to 0, then we know the shear and the moment has to be 0 at the free end of that beam. So that's another boundary condition we can use as we're solving these problems to solve for the shape of the bending deflection or the bending curve, the elastic curve of the beam. Finally, let's kind of synthesize this into like a mini example. So I'm going to take the case for a simply supported beam. Simply supported just means a pin at one side, a roller at the other. And I'll take a uniform distributed load on this segment. We'll say that the beam has a length of L. It will have two reactions, AY and BY. And let's go ahead and sketch the shear and moment diagram for this beam. A lot of times when we're coming up with boundary conditions and just the method of integration in general, it's useful to have the shear and moment diagrams because that might help us get a start on our problem. So we know for a simply supported beam, the shear diagram should look like this. It should be symmetric. And the value of the reaction, AY and BY, is going to be omega L over 2. So we see that the shear jumps up omega L over 2, it slopes linearly down to B, and then it jumps back up to 0. It crosses 0 at distance L over 2 from the support. Then we calculate the moment diagram. Again, we can take the area under the shear diagram. We get omega L over 2 times L over 2 times a half because it's a triangle. So that gives us omega L squared over 8 for our bending moment diagram. All right, so now I want to come up with the different boundary conditions that could exist for this problem. Now, we can come up with more boundary conditions than we need to solve for the bending deflection of the beam. That's okay. I just want some practice on coming up with boundary conditions, and then we can pick and choose which boundary conditions, because all these boundary conditions are true. And so since they're all true, then they're all valid conditions that we can use to solve them, at least from an engineering mechanics standpoint. So the first one we can take is looking at the shear diagram. V of 0 is omega L over 2. So that means EIY triple prime of 0 is also omega L over 2. We can also look at the moment. The moment at A at the beginning there is 0. So M of 0 equals 0. And so that translates to EI Y double prime of 0 equals 0. We can also look at the right-hand side of the beam at B. So we can write shear and moment conditions for what's happening at the right edge of the beam as well. We don't have to restrict ourselves to just the ends of the beam. We can look at any point along the length as long as the moment is continuous between those two locations. So let's look at m of L over 2. So we see that this value was omega L squared over 8. This would be another valid boundary condition for our beam to help us solve for the bending deflection. Finally, we'll look at our deflected shape. We know that the deflection has to be 0 at both the pin and the roller, so we get y of 0 equals 0. That would be the deflection at A equals 0. And I'll go ahead and make sure I add my letters in and add my coordinate axis in up there. And then we have y of L, which is the deflection at B, would also be 0. And that's another boundary condition for this particular problem. All right, we can also look at what's happening at the middle of the beam. Because of some symmetry in the beam, we see that the shear at L over 2 passes through 0, so we can use this as another boundary condition. Also, because of the symmetry of the problem, because both the supports are symmetrical and the loading on the beam is symmetrical, we also can take a look at the slope at the middle of the beam. The middle of the beam would experience the highest value of deflection, and therefore the slope would be at 0 at that point. It would be transitioning from sloping downward to sloping back up. And so we have a case where we have the slope at midspan. Now, we don't need all of these to solve our problem, but hopefully you understand where all of these values came from. I just, again, want to make the point that we usually, in a lot of cases, can't make any assumptions on the slope except for the fixed end, where we know the fixed end has a slope of 0. And only because of symmetry could we make this assumption, because of the symmetry of the load and the beam. All right, so I hope you understand boundary conditions. I'm looking forward to solving a problem with you. I'll see you in the next video.